Firstly, I would like to ask you some simple questions, like how many of you have done some kind of image processing on Android? That's great. And how many of you have done no image processing on Android, like no kind of? That's even better, because for this talk, you don't need any kind of background, because I'm sort of going to tell you the problems we faced while working on our app. So yeah, I am Garima Jain, and I work for a company called Over. It's a South Africa-based company, and we are developing an app which is called Over, which does like text over images, text over video, and those kind of things. So what is this talk about? You all must have seen various apps like Beauty Plus, Google Photos, or Instagram, wherein you can change your picture by just clicking at various options, and those are called filters. So this is what we're going to talk about in this app, like how to create these filters, and how we created these filters using a lookup table, and what kind of challenges that we faced. That was one kind of filters, and you must have also seen these advanced kind of effects that one can apply on your images. So these are also there, and like some apps give you a lot of different options. For example, this Lightroom app, wherein you can change hue, saturation, luminance, and you also get simple UI, wherein you could modify the curves and stuff, and those are like very advanced options and those kind of things. So that brings me to the first section of the talk, which is different approaches that we could have taken while developing these filters. So there are two different kind of options from a product point of view. So the first kind of option is presets, and the second kind of option is using LUT or baked-in filters. So what is presets? So this is like a way of storing filters. We can store filters either by storing like various kind of values that it could take, that is saturation, sharpness, luminance, etc. And this will lead to this kind of UI, wherein one would get multiple options, like one could change, as I mentioned, like luminance could be changed, and we could modify the curves and all those things. And these kind of features could be a little overwhelming for like normal users. They might not want to deal with all these kind of filters, because like these kind of features can grow. And also, what we wanted to do, the path that we wanted to take was, we were aiming for render parity across different platforms. And that is why, even though these kind of adjustments can achieve great results, and there are lots of customizable options, but do we even need it? Like, we can also do with something that is good for the user, and at the same time, we can also ship faster. So we went with the option of lookup table. So what is a lookup table that I'm talking about? It replaces all these kind of computations with simple array indexing operations. If we, for example, if I have this color, what color can I map to? This is a simple kind of a lookup table. So lookup table can have different types. For example, 1D, 3x1D, and 3D lookup tables. So this is a very simple lookup table, wherein we have 4 different indexes. 0 maps to one kind of intensity, and 1 maps to another kind of intensity. And on the right side, you will see that there is this intensity values which could range from 0 to 256. This is a very kind of this is a very useless kind of a lookup table. This is not used, but this is just there for explanation purposes. And then there is also a 3x1D, because when dealing with images, we just do not have one channel. We have 3 different channels. So we need a lookup values for all R, G, and B values. So we cannot just use 1D. And even this 3x1D lookup table is very limited. What we instead need is a 3D lookup table, wherein we can say that given R, G, and B value for particular, a combination of R, G, and B value, we want to map it to some other value, because that's what images are. They're not just 0, 0, 0 RGB or 1, 1, 1. They're a combination of values ranging from 0 to 255. So this is kind of a lookup table that we need. So if you see on the left-hand side, now we have that all sort of combinations for RGB, and those map to certain intensities. So if you look at this image, you'll see that this is sort of an identity lookup table. What identity lookup table means, just like an identity matrix, if we have an input image and we let it pass through this LUT, it will result in that particular image itself. So 0, 0 maps to black, and 333 in this case, because this is a 4 cross 4 lookup table, so 333 maps to a white. So good thing about this is we can specify lookup values for all sort of combinations of R, G, and B. So this is sort of the lookup table that we need. But even in real world, in practical life, 4 cross 4 cross 4 is not enough. And practically, 64 cross 64 cross 64 LUT images are used. 64 LUT images, they can map around 2 lakh colors. And we could also go with higher images like 256 cross 256, but those kind of images, they require a lot more memory to store, and so that is why we, practically this 64 LUT is used widely. So this is an example of how a 3D square LUT looks like. And let's look at the designer's pipeline. So what our designers need to do in this case is, they need to create all those filters, they can tweak all those values, those curves for us, and they start with this identity LUT square image, and they apply the same values to these LUT images, and then they export and create different LUTs, and thus they can create various different LUTs because they can apply all those filters to these images. And we as developers, we get these images and we need to process these images to filter to create different filters. But how we can do that? So when I started looking into this, I came upon this easy LUT library, and being the lazy developer I am, I was really happy to see this, because I get some library out of the box. But my colleague pointed out that this easy LUT library uses the Java API, which is called getPixel and set on CPU. And I had not seen these talks. These are very good talks, which if you're starting to work with image processing, I recommend watching them, so you'll not repeat the same mistake that I did of being so naive and using trusting a library which uses getPixel and setPixel, because this works on CPU and it is not that fast. And yeah, so it is not even so Gradle builds might be faster than this. So yeah, that brings me to even though these talks mention different kind of approaches to image processing, but still I'll hint upon different images for a brief moment of time. So first one is Java API that I just mentioned, getPixel and setPixel. And then one could also create filters in C, C++, but those are also not so much machine independent, and we cannot create for all sort of Android devices that we have. OpenGL, these also perform very well, and one could create very good filters with this. But again, those shaders, those are also not so much for all those Android devices. So there is this another option called Renderscript, which we also decided to use. So what this Renderscript does is, it is sort of a wrapper around the C99 language and gives us sort of goodies out of the box. And we can write small scripts which will run, if available, it will run on the GPU. And so we can do sort of complex computations in parallel for different pixels, because we have images, we have different pixels, we have lots and lots of pixels, and we want to process those pixels in parallelly. So Renderscript can do that for us. So let us look how we can do this with Renderscript. So with Renderscript, we have two options. Like, we can use either the baked-in intrinsics that Renderscript provides, or we can do our custom script. And of course, I first went with the script intrinsic because it is provided out of the box. Let's try it out. So this script intrinsic 3D LUT, because the name itself says 3D LUT, so it should be doing what we need it to do. So this is the definition right out of developer Android. So this is an intrinsic for converting RGB to RGBA by using a 3D lookup table. That looks good. The incoming RGB values are used as normalized XYZ coordinates into a 3D allocation. Not sure what that is. The 8 nearest values are sampled and linearly interpolated. Yeah, that looks great. And the result is placed in the output. So this looks like what I need. So I started looking at various APIs. So this had an API called setLUT. This is what I need, which takes in an allocation. What is an allocation? Allocation is Renderscript's way of saying that I want to allocate some memory to this Renderscript. Like, it saves us from the headache of malloc and killoc, because here we are dealing with C99. So this is what I needed. But the next question is, how do I create this allocation? So when I started looking at the API, I found various different kinds of APIs for creating an allocation. That is, create a cube map from bitmap, create simple create from bitmap. So firstly, the thing that came to my mind, because LUT is also sort of like a cube, so that must be what we wanted to do. So yeah, I was thinking about like which one to use. I started searching, and then I couldn't just understand, like, there are so many different APIs available, and the documentation doesn't like tell us exactly what we need. But then thankfully, I came upon this good GitHub repository. It is called EasyRS, which told me that I need to use this create typed. So what this repository gives us is, it gives us this data structure. This is all we need to care about now. And so this R size, G size, and H size, because we are using a 64 LUT, so those will be 64, 64, 64. Now I just need to figure out how to convert this square LUT into an integer array. And again, I started searching, how do I convert this? So I actually came upon this realization that we cannot even use like the square LUT. We need to use this horizontal strip kind of an LUT for this. And I used it. And this is sort of the code which sort of converts this square LUT strip into the integer array, which is pretty straightforward if you look at it. And then all we need to do is, we need to initialize this script intrinsic. This is actually the Java code that is provided to us. And if you see this last, we then said that allocation that we just created. And if you see that LUT script for each, this particular thing, this happens like in the background. This particular thing runs our small script, because we just did not create a script. And that script is created for us by script intrinsic 3D LUT. So by doing this, we can, like, very simple code, and we can just process the LUTs. That's great. And I was, again, very happy. And the good thing about working in a cross-platform team is, like, one cannot just write any simple code. We need to make it perfect. So somebody in the team pointed out, like, let's do some transparent tests. So within our cross-platform team, somebody did reference implementation wherein we had different kinds of bunch of input images and output images. And so I tried out this transparent test, and I had certain outputs to compare it with. So that is what I did. And this was the image I took, and it failed. So the reason why it failed is, like, it turns out script intrinsic 3D LUT cannot handle alpha images, and they should just put it in the developer documentation. And if we go back to the documentation, they actually did. I just didn't notice it. So it takes an RGB, and it converts into to RGBA. Like, I am still not sure, like, maybe it still can do alpha also, but like, it didn't work for me. So I decided to go the route of the second way, which is creating a custom script. So how do I create a custom script now? So if you remember, I told you earlier that script intrinsic class, that it creates the custom script for us, it does the initialization. Like, it would have been best if that worked out for me, because that also does some caching and stuff for me out of the box. But like, we always cannot get what we want. So I needed to create this custom script. So how do we create that? So so we iterate the whole image, and for each pixel value, what we do is we find the corresponding value in the LUT image, and then use that value instead of that pixel intensity. So we have an input image, and we have an LUT image. We repeat for all the pixel values. We get a pixel value that is RGB. We find the corresponding pixel value in the LUT image, and we save updated pixel value in the output bitmap. And we repeat this for all the pixel, and we get our pretty little output bitmap after we do this. So the interesting step over here is finding the corresponding pixel value in the LUT image. So let's look at how we can do this. Looking up a pixel value in LUT. So this is the square LUT that we started with. So this can be divided into red channel, green channel, and blue channel. So if you look closely, the red channel increases from left to right in each box, green channel increases from top to bottom, and the blue channel increases from the leftmost box to the rightmost bottom box. Yeah. Sorry about that. Yeah, so the blue value, so for example, if we take an input pixel, let it be 127, 127, 127, the blue value will give me which square to pick. Green and red value will give me which x and y to pick within the square. Like, if you at this point feel that, why do I need to listen to all this? You can just like quietly listen to it, and if in future you need to do this kind of computation, you can refer back to this talk, because like this information was very hard for me to find, and that is probably why I'm doing this talk. So we have an input pixel that is 127, 127, 127. 64 LUTs cannot process all 256 colors because they are 64 LUTs. So we need to divide the input pixel by 4. We divide it by 4, we get 31, 31, 31. So in order to find which square to pick, we get the blue value, that is 31st. And within that square, we need to go to the 31, 31 x and y position. So we get the 31st square. And within that square, we get 31, 31. And this is the intensity value that we need. We started with an RGB value, and we went to that particular intensity value in that lookup table. And this is the new intensity that we need. But my API understands only x and y, because like I need to provide it which x and y to pick. And as it turns out, this can give me the x and y. So if you look closely, blue is actually giving me the square, and I'm adding r to it. And again, blue is also, for y also, blue is giving me the square, and I'm adding g to it. And this particular code is written in C99. So what I'm doing is, like, I'm getting the element in LUT at x and y position, and this kind of out.rgb, this kind of goodies we get with Renderscript. It lets us do multiple operations, like updating all RGB values together, and there's more to it. And we're just putting the alpha as it is. So, yeah, and it works for us. So we just did this small pipeline. Let's put it through the transparent test. And it turns out it failed again. But like, why now this time? We have like taken the input alpha that we had, and we are using that. Why is this not working? So that made me, like, because I work in a cross-platform team, somebody pointed out that this could also be happening because they also went through the same kind of issues. So there is this something called pre-multiplied alpha. So when we have two transparent images, one over the other, what Android does for this is like sort of blending kind of a thing. So there is this blog called Curious Case of Android Pre-Multiplied Alpha, which explains this thing pretty well. So if we have this like destination, we want to, you can think of destination being the top image and source being the bottom image. So destination is multiplied by 256 minus the source alpha, and the source is multiplied by, that is the one behind, with the source dot alpha. So if you look closely, the source image is not going to change because we just added a destination image. So what Android does is, it sort of caches this value, source into R, source R value into R, into alpha. It sort of caches this value and makes it, sort of stores it as a pre-multiplied alpha R. And what is the issue with that? Because like we expected it to store proper RGB value, and instead it is storing a pre-multiplied value, which is not what we expected. It is storing a multiplication of alpha value. So the issue is, when we look up our input LUT value, we wanted to go to 127th value, but instead it's going to like the value, maybe 32 value. Or something, it depends upon the alpha, which values it goes to, so we get the wrong value lookup. So that was the issue with this. And the solution for this is, the first solution is we could load up the bitmap with this particular in pre-multiplied alpha, and that would load it up and not pre-multiply this. So Android also does it for a reason, and it does to improve performance. So instead, what we decided to go was like, we decided to handle it ourselves. So what we did is, we added a step within our pipeline. So when we get a pixel value, we will unpre-multiply it, sort of. So how do we do that? We just get the alpha, because we already know the alpha, and we sort of divide by the value that we get. So that is how we can unpre-multiply our alpha. And with that modified RGB and values, now we can calculate the x and y. And then we do again the same thing in input alpha. So we get the alpha from input and put it in output. And with this new x and y, we can look up the particular pixel. Okay, so that happened. This time, transparent test passed, and we are pretty happy about it. But not so fast. We still haven't reached the end. There is also something that happened. There is this banding and interpolation. So if you look closely at this image, this is the image we got for some of the filters. Like if you look closely, there's a little bit of banding over there. So why this is happening is, so let's, I briefly touched upon it, but let's look at it in a bit more detail. So we have an input image, and we have our LUT. So our input image for R, G, and B channels, they can take 0 to 255 values, but our LUTs can only map from 0 to 63 values because it is as I said, it is a 64 cross 64 LUT. So input image has like a lot of values, and LUT can only map 2 lakh colors. So so what we are doing is, like I mentioned in the example, we are dividing each R, G, and B values by 4, and that is how we're getting X and Y. So every 4 values are mapping to one value itself, and that is why we are getting that kind of banding. And because like, this clearly shows that it is a lossy technique. So how we can solve is, we can use interpolation. So this is a sort of a linear interpolation. If we have a value, a point, 6 0, y 0, and x 0, y 0, and x1, y1, we can sort of calculate the point in between. And because life is not so easy for us, we need to look at this kind of images and diagrams. So this is a cube again, and on the bottom left, we have R0, G0, and B0. So this is a picture taken out of this good book, which helped us and saved us. This is computational color technology. So this is a trilinear interpolation technique that we implemented. So given R0, G0, B0, and R1, G1, B1, we want to sort of find out some value in between. So if you need to look at the details, you can go ahead and read this book. Or like you can also look at this Wikipedia. It has a very good like small snippet to implement this. And we implemented this. So this was the image with banding, and we were with interpolation, we were able to reduce the banding, and this was the result, like compared to other things, were pretty good for us. So we went with this approach. And yeah, finally, it works. I promise this worked for us. So what we did was we added sort of another step in our pipeline. After finding a corresponding LUT, a pixel in the LUT, what we do is we also find some nearby pixels and we sort of interpolate them. And then we get the value instead of like just getting it from the LUT image. But like there were a few other issues, small hurdles that we faced. The first one was the Renderscript stack trace. So I was just playing around with my implementation, and I found out that my implementation was crashing for random cases, and we don't want that to happen. So I saw this kind of stack trace, and like it was really hard to debug this. But yeah, like I started taking hints from it, and if you see, there is some faulty address kind of a thing. And so while trying to debug this, like I came upon these good utilities. You can use them, but these utilities didn't work for me. So I just played on guesswork, and that faulty address, what that actually means is my app is sort of trying to access memory which doesn't belong to it. So I made a guess that where it could happen, it could only happen with arrays in C, because like we use pointers, and the pointer must be pointing somewhere else. So I started clamping those values, and it turns out my app stopped crashing. So yeah, that was the good approach. But yeah, like I did did some proofs for it. So yeah, it was like array index out of bounds, and like that was Renderscript's way of telling me. Anyway, the next hurdle that we faced is LUT formats. So this was the expectation. This is what we were talking about since the beginning of the talk. And this is the reality which our designers gave us. So yeah, I mean, we have been talking about this kind of LUT, square LUT since the beginning. But yeah, don't need to panic. Like, we can still handle this. So this kind of LUT is actually a HALD, H-A-L-D, HALD format LUT. I don't know what that is, but if you look closely again, there is this R, G, and B. So red values are increasing from left to right. Green values are increasing from left to right of the whole image, and blue is increasing from top to bottom. So that is a way to look at and like make sense of these LUT images. And again, if you remember the X and Y that we had, we calculate it a bit differently. Over here, this is the formula that we have. It was also a bit hard to find, and like, but yeah, like this is what we need to do. And so this particular step fits perfectly in our pipeline. So when finding the corresponding pixel in LUT image, instead of using the square format, we now use this. So we are happy and we implement it quickly. And finally, we get some good filters in our apps. I would like to say those are good. We could improve a bit on the speed, but yeah. So we have different format filters, and we have different intensities to play with. And yeah, finally it works. So this particular GIF has been taken from the app I work for. That is the Over app. So these are a few references that one could look at. And what next? There is this very good talk that my colleague did, Jain, which is building filters. He sort of implemented the reference implementation. One could also go and look at that. And there is also the formats that we just talked about, the HALD and square. There's also a cube format. I didn't go with this format, but we could also, if we want to make it more wide, more universal kind of an algorithm, we can also parse cube files. But those are a bit bulky, so I just didn't go with it. We could improve the speed of Renderscript even further, but like that's a sort of improving Renderscript implementation rather than this image filters. And we could go for an even better interpolation. I couldn't go ahead from that cube, like that was my limit, so that is what I implemented. So finally, sorry about that. So finally, I have this input image, and we have this different kind of LUT images, and we can create a lot of filters with it. So this brings us to the end of this talk. Any questions? Do we have time for questions?